it's Jenny, and today we're going to learn about hydrates.
When we produce dry compounds by evaporating water from a solution, we can be left with water molecules incorporated in the crystal structure. These compounds with water molecules incorporated in the structure are called hydrates. And this is due, of course, to the ionic charges of the compounds themselves and the geometry of the ions and of the water and the polarity of water, etc. One of these compounds is iron 2 sulfate, and iron 2 sulfate forms a heptahydrate. The idea being that every one formula unit of iron 2 sulfate has 7 waters attached to it. So they have each formula unit of iron 2 sulfate with 7 water molecules attached to it and incorporated in its crystal structure. When we go to calculate the molar mass here, just make sure we add the molar mass of all that water. So 151.8 for the iron sulfate and 126, which is 7 of those 18s from the water. So the total molar mass of this thing is 277.8 grams per mole. You need to pay attention to that additional water when you calculate the molar masses so that if you're making solution, for example, you get the right amount of it to get the concentration that you want. So such compounds can have this water of hydration, these bound water molecules, removed by strong heating. And this produces the compound in its what we call anhydrous state. So anhydrous means without water. So we want to determine how many water molecules are bound to each formula unit of the compound. Just think about that. There might be a case that several different hydrates are possible. So we'd like to know how many waters are attached to each one and determine which hydrate we're dealing with. So here's how we might determine the formula of a hydrate. So you'll definitely need some equipment for this. So here we have a crucible with a loose fitting lid. This crucible is ceramic because we're going to be heating that. And you'll need a balance with a hot plate insulation on the top of it. We don't want to damage the balance of the hot crucible, so we'll just put the insulator right on there. There's the insulator. And you'll also need a hot plate or stirring station. The stirring is not necessarily here, but we use a hot plate. You'll sometimes see this with a Bunsen burner, but frankly, I like a hot plate. Less chance to light your hair on fire. And so here's the equipment and here's the process. First, you need to zero the balance with the insulator, crucible, and lid all on there so that you're reading 0 mass. So I put that on there and zero the balance. Second, get some of the hydrated compound and place it in the crucible. So we're going to record the mass of that one too. So put the hydrate in there and record the mass of the hydrate there. So we'll just get this data going and we'll record the mass of the hydrate, and it is whatever it is. Then take the crucible and lid and hydrate and heat it up and mass it again. So mass it after heating and get a mass there. Heat it again, mass, heat, mass. Do this a couple times. Get the second mass after heating, do the third mass, and so on. Just keep going back and forth, heating and massing until you get the mass to stabilize. So if you were to graph the masses, we typically don't, but if you were, you would see the mass would fall here and eventually stabilize. And it would stabilize when all the water was removed. So they have the mass stabilized with the water removed. So once that's happened and the mass is stabilized, and it doesn't fall anymore after heating, then you can just make the safe assumption that all the water molecules have been driven out of the structure. So after this, we just need to calculate a little bit and determine the formula of our hydrate. So I think it's probably worthwhile to see an example. So let me just get an example going here. This one is a hydrate of copper 2 sulfate, and we want to determine what hydrate it is. So copper 2 sulfate with how many water molecules attached. So it'll be CuSO4 dot some number NH2O, and we want to know what that number of water molecules is. So here it is. We'll zero the crucible and lid on our balance and put our hydrated sample in there, and we got 1.300 grams of that stuff. Heat it, mass it after heating. We find we have just 0.84 grams. Some water's been lost. Heat it a few more times, mass it every time, and we got down here to 0.833 grams. That number's come up a couple times, maybe 3 times actually. We say, oh yes, the mass is now stable. So let's say the water lost was the original mass minus the final one. So make that 0.467 grams. And the mass of the anhydrous compound is obviously just 0.833 grams. It's left at the end. No excitement there. And now it's just an empirical formula calculation, really. So we'll just start with the copper sulfate here, and we know there were 0.833 grams of that, and it's 159.6 gram per mole, and we get there's 0.00522 moles. The water, we'll do the same thing, 0.467 grams, 18 grams per mole, and get 0.0259 moles. We'll make both of these relative to the copper sulfate, divide by that, and we get this 1 to 5 ratio. Looks to me like that's copper sulfate dot 5H2O, or copper 2 sulfate pentahydrate. 5, 5, and penta all belong together. So really that's about it for hydrates. Just empirical formula like anything else. And we're going to see these in our lab soon enough. And you certainly need to know how to handle making solutions using them. Anyway, that's about it. So thanks everyone. I sure do appreciate it. And see you soon. Do be sure to have a look at the next 2 videos in our playlist for more, and stay tuned for our next lesson, number 15, Introduction to Concentration.
This is my dad's YouTube channel. It's awesome. So like,